So in the last few classes, we learned how if a Boolean expression is given, how to simplify it using K-maps or using QM method and find an optimum solution, that is in terms of Boolean expression. Finally, what is the simplified expression? Okay, that is what we learned. Okay, but that is not adequate, right? You have to finally that simplified expression, whatever we got, needs to be implemented in hardware. So that is what we are going to learn today. So the topic is logic gate realization. That means first you have a problem statement. So depending on whatever is the problem statement, you will write a Boolean expression. Okay, that is the first step in digital design. So once you write that Boolean expression, that need not be a simplified version. It might be so many redundant terms might be there. So you will use a K-map method or a QM method and obtain a simplified expression. So the next step is to implement the excuse me, that simplified version into hardware. So that is what we are going to see here. Hardware means we are just going to see how to transform that expressions into gates. Okay, so that is what we are going to learn today. So if you see here, NAND and NOR gates are known as universal gates. Okay, they are known as the universal gates because any function can be expressed in that any other gate can be synthesized using a NAND and NOR gate. For especially for CMOS, okay, all other logics can be implemented using NAND and NOR gates. Okay, so this becomes that's why these are known as the universal gates. So if you have merely AND and OR, you cannot implement all the functions. Okay, NAND and NOR, either of them, not that you require both of them. Even if you have just NAND, all the functions can be implemented. Similarly, if you have just NOR, all the functions can be implemented. So these are known as the universal gates. In CMOS especially, NAND and NOR becomes the basic gates. Okay, AND is actually realized using a NAND gate and an inverter. Similarly, an OR gate is realized by using a NOR gate with an inverter. Okay. Now if you see here an inverter, okay, first let's see how to implement an inverter. So inverter is also can be implemented using an NAND gate. Okay, where if you see if you short the two inputs of a NAND gate, okay, it will start behaving like an inverter, isn't it? So if you see, this is a NAND gate, not AND, means 1 means it will give 0 out here, right? So that is the function of a NAND gate. So if you have input as 1, since both the inputs are shorted, if you have 1 here, you will have an output as 0. Okay, similarly, if you have an 0 here, 0 0, it is not AND, it will have, okay, a 1 here, but it's NAND. Okay, so it will given if it is 0 0, it will give an out. So this will act like an inverter. Okay, so you can consider you can make an inverter out of an 2 input NAND gates also, right? If you see an inverter also, you can consider it as an at the transistor level, you will just use 2 transistors and a single input. So you can consider it as an 1 input NAND gate also. Okay, not that if an inverter is in actual VLSI design, if I go into VLSI design, then if an inverter is to be implemented, I will straight away not make a 2 input NAND gate and make an inverter. I'll make a single input also. So this can also be implemented directly. Okay, so this is how with NAND we can implement an inverter. The other option is if you give one of the inputs as high, okay, as logic 1. So if you have 1 1 not AND, so you will get 0, and 1 0, the input is 0, since it's not AND, it will give output as 1. So this way also inverter can be implemented. So these are the two configurations of NAND to implement an inverter. Similarly, NOR also, if you tie both the inputs together here, if you see a 0, okay, so for an OR 0 0 will be 0, and then it is a NOR. So this bubble indicates it's an inverter, like, so NOR, it is not an OR, it is a NOR. So 0 will become 1. So if you have an input 0, you will get a 1 here. If you have 1 1, so the output of an OR will be 1 and NOR will be 0, so it will get inverted. So this is also one option of implementing inverter with NOR gates. Or other configuration is where you ground this one. So right, so if you have this is ground, so if you have input as 1, OR gate will be 1 and NOR gate, again you have a bubble here, it will get 0. So this is another configuration. So these are the 4 different configurations of implementing an inverter using either NAND or NOR. Okay, is it okay with all of you? Yeah. Okay. So these are the other NAND implementations. Okay, this we saw how an inverter can be designed. Okay, what is a buffer? And a buffer is like you have the same A and you have an same A coming out. Okay, and this is generally used many a times to isolate the input and output. And so this will be generally when we say buffer, the output NAND will have an higher current carrying capacity. Okay, so that if you have to drive an huge load, so this buffer capacity will be often higher. This is generally applicable to VLSI circuits. Within a circuit, and when you are implementing certain functions, you will not have large size inverters, but in the output stage you generally connect a buffer. Okay, buffer will generally have an higher current carrying capacity. Okay, so this is not so you can implement a buffer by connecting 2 inverters back to back. The second inverter can have an higher current carrying capacity. So here this function which we have generated, that doesn't get loaded by the external loads. Okay, so that is what a buffer is. Now similarly, an OR gate, if it is required to be implemented with an NAND gate, if you see here, you have an AND gate here, right, a NAND gate here. So the inputs are inverted here, right? If the inputs are inverted here, so it will become an OR gate. Okay, so if you see here, A bar, B bar. Okay, now this is an AND gate, and then you have a bubble out here, so that becomes NAND. So before the bubble, what you have is an A bar and B bar, and since it's a bubble, you will use De Morgan's theorem. So A bar, B bar, the whole bar, so you will get A plus B, right? A or B. So this is the way you can implement an OR gate using only NAND gates. Similarly, if you want to have a NOR gate, then you first make an OR and then again put one more NAND inverter. So these are similarly you can make an XOR gate, exclusive OR gate also, exclusive NOR gate, exclusive OR gate. Okay, the difference between these two is exclusive OR is for 0 0 you get 0, 0 1 and 1 0 you get 1, and for 1 1 you get 0. Exclusive NOR is for 0 0 and 1 1 you get 1, and for 0 1 and 1 0 you get 0. So you can just verify how these gates functions by trying to give some inputs out here and trying to visualize what is the outputs available. So you will find all these different kinds of functions can be implemented using an NAND gates. Similarly, we can have NOR implementations also, and that means all the various functions can be implemented using a NOR gate also. So this, the first one we have already seen. We can make an inverter by shorting the 2 inputs. So this is a NOR gate, and if you short both the inputs, then it will act like an inverter. If you want to have an OR gate, so you use an OR gate and followed by an inverter. Okay, so the inverter is realized here by shorting the 2 inputs out here. So and buffer is again, if you see here, these 2 inverters. This is an inverter, both get shorted. This is also another inverter. So you use buffer means if you give A, output will be A again. Okay, now like I said, in this case also, whenever you have to drive large external loads, you use a buffer with the second NOR gate, which is capable of giving high current. So this is specific, more specific. Like in case of microprocessors also you can use this. Like suppose a microprocessor is giving an output and you want to drive an LED or things like that. You don't want that LED or a bulb directly to be connected to the microprocessor input pin, because it might load the microprocessor. So in between you can use these kind of gates, right? So this could be a TTL gate, okay, external IC. You can just put an NOR IC there. So now that LED will be driven by this TTL gate, right? And it will not load the microprocessor. So you have isolated the microprocessor and the load by using an TTL gate in between, right? This is it. So these kind of things that is the application of a buffer. One more application which I just mentioned. Okay. Similarly, you can have an AND gate. So if you see here, what is being done, you are creating A bar and B bar and you are giving it to a NOR gate. So A bar, B bar, so output of the OR gate will be A bar or B bar, and since you have a bubble here which is a NOR, so A bar or B bar, the whole bar, and by applying De Morgan's theorem, that turns out to be A dot B or A and B. So this is how you can now synthesize an AND gate using only NOR gates. Similarly, if you have to have a NAND gate, first you synthesize AND and then you put an inverter again. Similarly, you can have an XOR gate and or an exclusive NOR gate also using only NOR gates. So in short, in the last two slides, what we have seen is with the help of only NAND or only NOR, all functions can be generated. Okay. So now if you see, these are the three configurations which are important for us to know for transforming the Boolean expressions which we the simplified Boolean expressions which we obtain using K-maps or QM method. So all these implementations, and you need not remember, but these three you have to remember. Okay, so to make an inverter, okay, for NAND you just short the two inputs and you get an output. Okay, and then to make an AND gate, so you have a NAND followed by an inverter. Okay, because now when we make an simplification of a Boolean expression in K maps, okay, if you are going to simplify the min terms, we are going to get a function in the term like in sum of product forms, right? So you will have AND and OR only there, right? And you will also have some complements of certain functions, so you will require. So these three are only the transformations are required for you for transforming any K-map min terms into simplified min terms using K-maps into an logic circuits include implementation with NAND. Okay, so these are the three transfer. Now if you see an OR gate out here, okay, this is an OR gate. If I have to implement with an NAND, okay, this is A, this is B, so two inverters are there, so I put two inverters there, so this becomes an A dash and B dash. Okay, now this is what A dash B dash whole dash, right? So this is A dash B dash whole dash, because this is NAND, right? So which turns out to be, okay, De Morgan's theorem. So you can bring this inside, so this AND will become OR, so this final expression comes out to be A or B. So an OR gate can be implemented like this using a NAND gate. So if you remember these three transformations, that will be good enough for the time being for implementation of the truth table results into NAND implementation. Okay, now suppose I have to implement a function AB plus BC. This is the simplified function which I finally get. Now I need to implement it in hardware. So this is what, right? AB, BC and an OR gate. So how to transform this into an NAND gate implementation? So first what we do is replace each of the gate by its corresponding NAND realization. Okay, so this is AND. This is NAND, this is OR. So we need to replace each of them with the NAND realization. So the first AND gate we have replaced with a NAND followed by an inverter. BC is again NAND followed by an inverter. Okay, so is this much clear, Sachin? Okay, this is the function which we got from the K map. Now we have first made NAND OR implementation. Now we have just replaced these two gates with a NAND followed by an inverter, right? So this becomes AND, right? So this is what we have done. And now for this OR gate, what did we see? An OR gate is nothing but NAND gate. The inputs have to be transformed. If I go back to the previous slide, this is what an OR gate, right? The inputs will be inverted, and then you put a NAND gate there. Okay, so that becomes OR gate. So here now what I have done, this OR gate I have replaced with two inverters followed by an NAND gate. Now if you see here in this particular diagram, this is inverter, this is inverter, this is again an inverter followed by an inverter. So I can just remove these inverters out here straight away, and I can draw it like this. So this is the same AB plus BC has been implemented using NAND gate. So this is the final solution for me. So if you see here, if you have AND OR combination like this, simply I changed it with NAND gates, it is going to be the same function. Is this clear to all of you? Divyanshu, anybody can just prompt whether it's clear or no. If need be, I can repeat it once more. We are going to ground one of the logic gates. In which scenario are we ground one input of the here we are not talking about grounding. I said the grounding is in case you need to here, like in case you have to implement an inverter, in that case with an OR gate you can do this, okay. But right now we are not doing that. We are not grounding anything out here. So this is the function which we need to implement it. So how to go about that is, first AND gate we are replacing it with the NAND gates, because we are looking at implementation of a function. The problem is, first we make a K map. From the K map we get an expression. From the expression we straight away draw a circuit with AND and OR. So this is known as the sum of products. Okay, this is product, this is sum of product form. So we straight away implement with AND OR gates, and then slowly replace each of these AND gates with the corresponding NAND implementation. So this particular is NAND followed by an inverter. This AND is NAND followed by an inverter. This OR is NAND prefixed by the inputs are prefixed by an inverter. So I have made this, and now I have cancelled these two inverters and obtained an simplified NAND implementation. Is it okay now? Okay. So this is one option. Now the second option of doing it, suppose I have an AB plus BC. This is the function which first I have got this expression. With that I have implemented an AND OR implementation. Then I put a bubble. Okay, I have to make this as a NAND gate, right? So I put a bubble out here. Okay, so this becomes a NAND. So I put a bubble here. This becomes a NAND. Now bubble indicates an inverter. Okay, so to compensate this bubble, I put one bubble here. To compensate this, I put one more bubble here, right? Now what is this? It's an inverter. It's an OR gate with bubbles at the input. Okay, what is that? If I go back here, okay, an OR gate, not this. Okay, and okay, that I have not explained. Okay, if I put an two bubbles at the OR gate, okay, what would it happen, right? If I try to put two bubbles in the input of an OR gate, okay, that will again be an NAND gate. Okay, because if you see here 0 0, it will become 1 1, right? For 0 0, it will become 1 1. The output will be 1. So that is NAND gate output only. If I put 1 0 or 0 1, also it will be 0. Or if I put when I put 1 1 here, okay, it will be 1 here, right? And then when I put 1 1, because there are two inverters which I have put in the OR, that will become 0 0, and the output will become 0. So that will become a NAND gate. So that property we are using here. if you put an OR gate and if I put two bubbles out here, right, then this will become like a NAND gate. Okay. So if you remember the duality principle, okay, we learnt that if we invert all the inputs, then AND will become NOT and NOT, AND will become OR and OR will become NAND if you invert the inputs, right? That is the duality principle. Here also, and the output also, input and output, if they are going to be inverted, then OR can be replaced by a NAND. So if you see here, I am inverting the inputs. Okay, if I put a bubble out here, okay, one more bubble out here, then this can be replaced by an AND gate. But since I am not putting a bubble here, this will become a NAND gate. Okay, so if I keep it things very simple, if I have an OR gate and if I just invert the inputs, it will become a NAND gate. If I keep that very simple, so you can just verify that using the truth table also. Okay, so I can straight away, instead of doing this thing out here, okay, so the bubble procedure is pretty simple. Okay, first you put a bubble here, you put a bubble here. To compensate that bubble, you have put one bubble here, I have put one more bubble here. So it is an OR gate. If the inputs of an OR gate are inverted, that becomes a NAND gate. Is this clear to all of you? Yeah, Kishan, is it okay? Divyanshu? Okay. Okay. Now, if you see here, we'll take one more example, so things will be even more clear. Now, this is a NAND gate realization. So this is the function which I need to make. Okay, this is the expression which needs to be implemented in hardware. So I have A. First, I have a B, C dash. So you have a B, C dash, and AND gate, Okay, and then you have an OR here, and here you have a CD and AND gate, and then which is getting OR with OR, and then you have one more AND with A here, and then finally you have an OR gate. So this is the gate. Now I need to this is what I get after simplification. Suppose this is what I am getting after simplification, then I need to, now this is AND OR, I have only NAND gate, so I need to redraw this circuit using only NAND gates. So what do I do? Okay, so let me use the bubble technique. Okay, so first I am going to put a bubble out here for this here on top. So this bubble here, to compensate that, I have put one more bubble here, right? Now now I am going, because I need to transform this also into NAND, right? So how do I do that? If both the inputs are inverted, then I can replace this as a NAND gate. So I put a bubble out here. Now if I have to put a bubble out here, this was B here, now this has become B dash. So I have to take an B dash out here, right? Okay, so these two gates are taken care of. Now I have an AND gate here, so I put a bubble here, so this becomes NAND. Now to compensate that, I have to put one more bubble out here. Okay, so I put a bubble out here, okay, to compensate this bubble. Now this is an OR gate. Now to make this a NAND, I have to put one more bubble here, so I put one more bubble here, and to compensate that, I put this is an this was an AND, so I put one more bubble here, right? Now if you see here, from here, if you see now this bubble along with this AND, this has become NAND. This bubble which was there in the input of this OR gate, so that has become a NAND gate out here. So this bubble remains here. Again, this was an OR gate with the two bubbles in the input, so that has become a NAND gate. Okay, so this bubble with along with this AND gate, that becomes a NAND gate. Is this clear to all of you? Yeah, Ritika, Divyanshu, is this how this circuit has come from here? Is it okay with all of you?
Sir, why B become B dash in second circuit?
Yeah, okay. See, first this is an AND circuit. This is an AND. Now I need to make it a NAND, so I put one bubble out here, right? Okay. Now I can't put just a bubble like that, right? To compensate that, I have put one more bubble here. So in the input of the OR gate, I have one bubble. Now I need to implement everything as NAND gate. So I know that if I invert the inputs of an OR gate, then that will become a NAND gate. Okay, so I put a bubble here. So I can't just put a bubble right here. So this bubble requires to be cancelled. If you see here, from the top to bottom, I have put two bubbles in series. So that is why they cancel each other. So it is not going to make any change in the function. Whereas here I have put a bubble. If I don't put one more bubble, then the function will change, right? So that is why I have changed B to B dash. Is it okay?
Yes, I got it.
Okay, so the function cannot change. So every bubble which we insert needs to be compensated. Okay, now this is an AND gate. Okay, here we are not inserting any bubble here. So this remains, this A is coming as it is. Here we have inserted one additional bubble. To compensate that, I have put one more bubble here to the input of the OR gate. Now to make this OR gate NAND, I have put one more bubble here. To compensate for that bubble, I have put one more bubble here. So all the bubbles should be in pair. Okay, so this is a single bubble out here. So I have changed this into B dash. Okay, or you can put an inverter out here, or you can use an NAND gate. If you want to still use only B, if suppose only B is available, then I need to put an NAND gate here with two inputs shorted, then I can use B. Okay, so every bubble requires to be compensated so that the final output doesn't change. Okay, so this is how we get the final output. Is it okay now? Yeah, okay. So let's move forward. So suppose this is an K map out here. So the function what we are getting it, this we saw in the previous class. Suppose the function is A plus B dash CD. Now this we need to implement. So the first step what we are going to do is we are going to write A or B dash. So B dash has been generated, then CD. So this is the implementation with AND OR. Having done that, now we try to implement the same function using only NAND. Okay, so if you see here, B is here. We need to this NOT has been replaced by an NAND gate, input shorted. So this will become this NOT has been replaced by a NAND gate. Now I have an AND gate here, so I put one bubble out here. Right, if I put a one bubble out here, so here also it's an OR gate, so I have to put one more bubble here, so one more bubble here, so this has to become A bar. So instead of since here all the inputs are bar is not given here, we are assuming that only the function is available, the complementary function is not available, so we are generating the complementary function. So I have one inverter which is placed here. Is this clear to all of you? Okay, try to understand this thing very clearly, because in the exam finally if a expression will be given, you will have to make a K map, and from K map you will have to finally draw this NAND implementation. So this entire process should be clear to all of you. Is it clear? Yeah, Mariam, is it okay? Yeah, okay.
Yes, sir.
Okay.
And so one more thing, like in exams, we will be, given the problem with the, like they will be written, like we have to implement with NAND implementation.
Yeah, they could be like, yeah, they could be an expression which will either like an f is equal to certain min terms is given here. So you will have to implement it with NAND gate. So if you have given a min terms, you might have to draw an K map like this, right? And then you might have to solve it for a midsum. I'm talking about midsum. So you might have to solve like this, right, using the K maps, and use finally from the K maps you will have to AND OR implementation, and then from there you might have to make the NAND implementation. Okay.
Okay, sir.
Yeah. It's pretty simple, and these things are very logical. So I think once you have a look, you will not have any problem, right? So like we said, when we are, if you remember what was being what we learned in the last class, we can also collect the max terms, and when you collect all the max terms, you will get an expression like this, right? Now here all the ones were grouped, and if you try to club all the zeros, right? If you try to collect all the zeros, you will get a expression something like this, right? That is max term. So we did a few examples of that. So a plus b, a or b, and c or d. I think this bracket is not required. So you have this or expression, or and an AND gate implementation. Now if you have this, can be implemented with NOR gates, okay, in such cases. Okay, what we need to do is we put a bubble out here, so this OR will become NOR, and like we said, in the OR gate, if you invert the inputs, it becomes NAND. Similarly, in an AND gate, if you invert the inputs, it will become an NOR. So this becomes an simple NOR gate implementation, right? So if I give a function like this, max terms, and then I ask you to implement using NOR gates, what you need to do is, if I give a function, even if I give a min terms, okay, I give the min terms and then ask you to implement using NOR gate, what you need to do is, you will have to since the implementation is with NOR gate, now you need to find out the product of sums. Okay, now you have to group these zeros here. Now if you see here, if you group all these 4 zeros, what is the expression which you will get? If you remember from the previous class, if you take these 4, okay, it is like A is 0 here in both these cases, and this C is 0, so it is an A dash and C dash, but we are going to write it as an A plus C. So this is going to, this 4 is going to be A plus C. Similarly, this 4 is going to be A plus B bar. Okay, and these 4 and these 2 and these 2 also can be clubbed, and you will get an expression. So you will get in this particular format if you are going to club all the zeros in the K maps. So and once you write in the product of some format, then the implementation will be OR and NAND, and then from there you can make it a NOR implementation. Is it clear to all of you? Okay, from here we get the NOR implementation. So this also can be done. So now we know for any given function, okay, you can either finally draw a NAND implementation or a NOR implementation. If you have to implement only with NAND, then I make a K map with all ones and then make this and follow here. And if I have to do a NOR implementation, I will take all the zeros and write an expression in this form. This is known as product of sums, and then I make with OR and AND, and then replace it with an all NOR gates. So these are the two kind of implementations which is possible, okay, for any Boolean expressions. Okay, now let's take some practical examples. This is nothing but a majority carrier, you can say. There are 3 individuals, and some proposal is given. If 2 of them say okay, the proposal will be assumed as final. Okay, now if you see here, whenever there are 2 S coming in, the proposal will be F. Okay, now here also, if you see here, 2 of them are giving S, so the output proposal is S. So here all the 3 are giving 1. So now how to implement this circuit, right? You could have like 3 people sitting in 3 desks, and you have an switch available, and finally you have a light which glows up if more than 2 are pressing the switch. Okay, so you make an K map here, so you get an expression which we did in our lab also. F is equal to yx plus yz plus, so you have you make this K map and you have these 3 expressions, right? Any 2 of them are 1, then the final output will be 1. So this this final one is redundant, right? All the 3 combination. So even if you make from the K map, it can be seen that these 3 combinations, if you take, and you can implement the function. Okay, now how to implement in hardware? If you see here, this is an and 3 and 1 OR. So 3 and 1 OR gate, then you can put a light out here. Okay. Now when you give the connections to the switches, you need to use this is known as an single throw double pole switch. Okay, double pole means you are throwing it here or here. When you are throwing it onto the top position, okay, you have a VCC going here, right? This is for the person 1, okay, individual X. If he puts it here, okay, it will be 1 here. If he puts it down here, right, you can't use in this particular circuit like normal switches what we have in our home. Like if you switch it off, nothing will go. What is nothing here? If you have a wire hanging here, okay, without giving any input, then this particular AND gate may not give the correct answer, okay, because the wire is hanging. So when you're putting it into the second position, so this switch has got two positions. In one position you will give VCC, and when you are switching it off, okay, so yeah, it will be ground will be going here. So if you see here on this particular wire, there is only two possible voltages which is available. One is VCC, the other is ground. There is no hanging. Okay, so if you use the common switches which is there in our homes, okay, then there will be an error in the circuit. Okay, because the common circuits is just a make and break switch, that is known as single pole single throw switch. This is single pole double single throw double pole switch. That means when you are putting it into the off position, also to the output 1 volt here ground is available here. Yeah, is this clear? Why are we using these kind of switches? Yeah, Kishan, is it okay? So when you're doing practical implementations,
Yes,
you
sir.
got to be careful, right? Yeah, you can't have a hanging wire here, right? So these are the kind of switches which are these kind of switches are also available in the market. So you need to use these kind of switches. Okay, so at any given point of time, the inputs will be either 0 or 1. It will not be hanging, like no connection at all. So that kind of things we should not do it with digital gates. Okay, because if it is hanging, so you are not telling the gate whether it is 0 or 1, it is just hanging. So hanging not necessarily means 0. Okay, you got to understand that. Okay, but in case you have those kind of switches, okay, which has got single pole and single throw switches, still you can use it, but you need to use it in this particular configuration. So this is for an OR gate. If you see here, this is plus 5 volts, say VCC. You have connected, say, one resistance out here, one resistance out here. Okay, this is permanently connected here. Now in this particular case, if this switch is open, what will be the input to these gates? Anybody? These switches are open. So is it logical 1 to both the gates? Yeah, Divyanshu. These switches are open. Okay, so if they are open, what will be the output? Output will be 1, right? Because you have connected VCC through these resistances. So these gates, if you see here, they consume negligible power, so there will be negligible current in these resistances. Okay, so the high voltage, so the entire, there will be negligible drop across these resistances, so it will take as logical 1, so the output will be 1. So the moment you are closing either, so this is OR gate, right? So if you put an if you close this switch, okay, what will happen is, suppose I am closing the switch A, so a current will flow from VCC through this R1 to the ground. So all the voltage which is was available, that will fall, that will get because of an IR drop. So the voltage will drop across R1. So you have this ground coming here, so it will become 0 here. So similarly B also, whenever you switch it on, B will become 0 here. So off means A equal to 1. In this case, B is off. This switch in the off position means 0. In the on position, it means 1. So this way you can implement it. Okay, so these switches. So this is okay. Even if you have In this case you have a single pole single throw switches. Okay. Similarly, you can have this configuration also. Here if you see the resistance and then there is a ground here. So if the switch is off, obviously the ground will be available to these, so it will be 0 0 here. The moment switch is closed here, this voltage will be available out here, right? So you need to use these resistances. Okay, if you don't use this resistance, what happens? The moment you switch it on, this particular VCC will get connected to ground. Okay, and then your power supply will get shorted to the ground. So you use these resistances to restrict the current flow, right, from the VCC to ground. So these could be seen even mega ohms also, no problem. In this case also, right, if you don't use these resistances, if you close this switch, the VCC will get shorted. So you need to use these resistances. Okay, they are known as pull-up resistors. In this case, they are known as pull-down resistors. Okay, so they are generally of the order of a few mega ohms. Okay, so this is how we implement gate in practical. If you have to design something in the practical life on a PCB, so these kind of things can be done using when we are using switches. Okay, so if you see here, when you are using TTL gates, although we have not time being don't get too much of a details into it, I am just casually mentioning these things. Subsequently, toward the end of the course, we will learn in detail about the TTL gates. Then these things will be very clear. In TTL gates, if you do see, this is how a TTL NAND looks like. Okay, you have an BJT where you have the emitter connections available as inputs. Okay, so the moment I give a 0 in any of these inputs, okay, this is a NOR gate, a TTL NOR gate. If I give a 0 here, then the current will start flowing like this. Okay, and then since the current is going to flow like this, this transistor will switch on and it will drive this transistor off and the output will go high. So if you see in a this explanation in detail we will see later on. So for this transistor, whenever I want, this is a NOR gate, so whenever I give a 0 either at A or B, okay, so then this transistor will get switched on and the output will go high. Okay, so that is how it works like a NOR gate. Now in this particular case, and if it is 1, both the inputs are 1, then this transistor remains off, because you have 1 here and you have 1 here. So this both 1 1, there is no potential drop across the emitter and the base. So this transistor remains off. So even if there this transistor will become on when one of the inputs is 0. Okay, so in this particular case, if you see here, if you leave these terminals open, okay, if you leave it open in the TTL gates, it will consider it as 1, because only when you give a proper ground, this will the current will flow here. So if you give an 1 here, 1 and 1 here, it will not allow current to flow here. If you leave it open also, it is the same thing, it will not allow current to flow here. So for especially for a TTL gate, okay, generally you might think that if you don't give any input, it will be considered as an 0. That's not the case for TTL gates. For TTL gates, if you don't give any connection in any of the input terminals, it will be considered as 1. Okay, so that we'll see in much details in the towards of the end of the class. So you have to remember that. So when you are doing a practical implementation with TTL gates, if you are leaving any of the inputs open, then it will be considered as 1. In our simulation, in LT Spice, and it doesn't cater for that kind of practical aspect. There, if you leave it open, it might considered as 0. But actually, if you are going to implement it on a breadboard, then you will or a PCB, then you will see that if you use the if you leave the input open, it is going to take as 1. For that is only for TTL gates. Okay, for other families of, like for CMOS, the things will be different. Okay, I am talking only about TTL gates. Okay. So this is, in this case, you need not use these pull-up resistors, because if you close this switch, it will be 0. If you open it, open is 1 for a TTL gate. So in this case, these pull-up resistances are not required. Okay, so these are all certain practical aspects which I am discussing in the class, not really required for your exam, but if you are going to actually design something in future, so these things will be helpful. Okay, now this is important even for your exam point of view. So now what, suppose I have to design a 7-segment decoder. Okay, what is a 7-segment decoder? The after the computation from the microprocessor or something, the output is in binary form. Okay, and I have to lit up a 7-segment display. These 7-segment displays you might have seen everywhere, right? It's there in your calculator. Okay, or you see the time. A lot of places the clocks are available. Okay, which is displaying the time, and in railway stations and many places you will find these kind of displays, right? So so you have this is to be, if you see here, there are 7 different segments. Okay, A, B, C, D, E, F and G. Now if I have to display 0, then I'll have to light up A, B, C, D, E and F, and G will be off for 0. Similarly, if I have to have 1 here, then B and C will be lit up, and A, F, G, C, G, E and D will be off. If I have to have 2, A, B, G, E, D will be lit up, and F and C will be in the off condition. So for different input combination, different LEDs segments will be the different segments will have to be switched on. Okay, so you have the inputs. Now if you see, since the output can have only from 0 to 9, right, only 10 values total. Okay, so the input will be from all the 16 different input combinations is not required here. The input combination will be restricted from 0 to 9 value out here. Now how to design this particular, although this ICs are available in the market, let's see now how these ICs are designed. Now if you see here, A, B, C, D, these are the 4 inputs. Okay, A, B, C, D. These are the 4 inputs A, B, C, D, and these are the various light segments. Okay, 7-segment displays. For 0, if you see, all are 1 and G is 0, right? This element in between which is there, this is 0. Similarly, for 0, 0, 0, 1, A is 0, B and C are 1. Okay, B and C are 1. So you make an table like this. Okay, for various displays. Okay, so these are A, B, C, D, E, F, G. Now if you see here, this is the input, now this is the output. There are 7 different functions out here, right? So we can make 7 different truth tables. This is truth table for A. Okay, this is truth table for B, this is truth table for C, right? So we can make for D, E and F, and for each of the truth table, only 9 inputs are we are taking, rest of that are don't care, because 10 to 15 is not likely to be there in the as an input. So we are making it at don't care condition. Then you can simplify the expression from the K maps for A, B, C, D, E and F, right, and G. So we simplify it. Once we get the simplified expression, we can implement the with AND OR gates, and subsequently if required we can make it with NAND gate also. So what are the design steps involved? Have you understood, all of you? Right, these are the 4 inputs, right? These are the 4 different inputs. These are the 7 LED segments which are there, right? 7 segments. Okay, for each of them corresponding for each input combination which light has to glow, I make a table out here, and for these each I will consider as an output. Okay, so for each of them I make an K map. I am taking don't care for 10 to 15 the input values. Okay, because this is a 7-segment display, the display will be from 0 to 9, so 10 to 15 are don't care conditions. I put don't care and I simplify for each one of them, so I get a simplified expression for A, B, C, D, E and F and G. And then if you see here, this is A, this is A bar, B, B bar, C, C bar, D, D bar, and then I use that expression. Like if you see here, if I go A, this is the expression A after simplification. What I got is A or C, BD and B dash D dash. Okay. Now if I go here, this is an OR gate, right? So if you see here, this is an OR gate. So 1, 2, 3. Okay, where is A? 1, 2, 3, 4. Now 4 input OR gate, and A and C and B, BD and B dash C. So if I see here, this is an A. So I have an A coming here, and I have C coming right here. I have C coming here, and then B coming here, D dash and B dash D dash. Okay, so this is how this A has been generated. Similarly for B, C, D and F. Is it clear to all of you? Yeah, Kishan, is it okay? Divyanshu? Okay, so if a function is given, so this is how we go about first making the K map and then making the circuit out here. Okay. Now many a times when you are making practical circuits, okay, when you are using mechanical switches, what happens is, say this is a mechanical switch. Okay, now if you you are throwing this switch from position A to position B. So when this switch is coming to position B, okay, it's a mechanical switch, right? Once it goes and makes a contact there, it is not going to make a smooth contact. It is going to touch there, come out again, make a, because it will all be spring loaded. So if you see try to see the output out here, it will go to 5 volt, again it will come down. So you will have these kind of spikes at the output, which is generally not good for any circuit. Okay, because this is a mechanical switch. Okay, whatever switch you implement in mechanically, when you are putting it from 0 to 1 or 1 to 0, it will just not go and get stuck there, because it is mechanical spring loaded. It will go and always do some chattering there. Okay, it will go touch that terminal, bounce back, again touch back. So these kind of things will this is known as bouncing. Okay, switch bouncing. So if you all mechanical switches, in fact, when you have like this, very rarely will it happen that it will go and make an contact in the first go and remain like that. So more often than not, then you will find these kind of bouncing happening in the mechanical switches. Okay, so to avoid that, we have something known as a debouncing switch. Okay, so this is known as a debouncing switch, which is implemented with two NAND gates which are cross connected like this. Okay, now if you see here, now suppose this switch is initially in the A position. Okay, so B you will find is open out here, but since there is a pull up resistor here, this 5 volt is available to this NAND gate, and since this is in the A position initially switch, you will have a 0 coming here. So 0 means this will also become 1 here. So this 1 is available here from here. So 1 is available here, this is 0 here. So that 0 is available here. So it will remain stable. Right, if you try to analyze what is happening in the stable condition, you have a 0 here, this is 0 here, so this is 1 available here, this 1 is available here. Now 1 is already available from this position, this 1 is available here, so that makes it 1 here makes a 0 here, so that feedback is given here, 0 here. So it is in a stable condition. So as long as you don't disturb this switch, here the output will be 0 out here. Now the moment I turn this switch to the B position, okay, the first time it makes an contact with B, what happens? The very first time it makes an contact with B out here, right, this will become 0 here, right. So now this will become 0 here. The moment it becomes 0 here, this is not AND, so this will become 1 here. So I have 1 coming here, right, and now this switch is thrown from here, so you have 1 here. So this 1 will become 0 here, this 0 is available out here, so this 0 will make this as 1 here. Now this switch is going to position B, it is going to bounce back from there, again going to touch back B, but that bouncing will not affect the output. Okay, why? Because the first time it has made contact here, a 0 is available here. Okay, that 0 gets transformed as 1 out here, that 1 comes here, okay, and that one creates one more 0 here, and the 0 is available from here now. So even if this switch goes there, it bounces and again touches back 2-3 times, doesn't matter, because the first 0 which came here, okay, that gets transformed into, okay, 1 out here, and then that creates an additional 0 here. That 0 is available here. So if you will find that the output is smooth, there is no bouncing happening here, right? So this is known as debouncing switch, because this switch, once you throw it B, it will go touch B, come out a little bit, it will not come back to A, it will go and touch B, move out of B, again go and touch B 2-3 times, it will make the contacts, but that will not get reflected as spikes in the output, because this is known as the debouncing switches. So whenever you are designing practical circuits with switches, okay, if it is a critical application, like if you are giving this input to a microprocessor, okay, then you might want to use a debouncing switch like this. Okay, what the debouncing switch is like, if A is like here, B is changing from, so there is going to some chatter, but the output of Q, it is not going to have that kind of an chatter or unwanted transitions. Okay, so this will remove all these unwanted transitions. So this is known as an debouncing switch. Okay, so this aspect I just covered, so that in case tomorrow, sometime in future, if you are going to use manual switches to give input to a microprocessor, then you might want to use an debouncing switch like this. Okay, so with this we come to end of this session. We will take a 10 minutes break, and followed that by that we will take a small topic of around 10 slides on hazards. Okay, thanks a lot. So we will